Hello viewers, in today's session we are going to discuss another important inequality from application of derivatives. So here in this session we'll prove this important inequality that is the natural log of 1 plus x square is less than x for x greater than 0. So here we'll make use of the concept of increasing and decreasing functions to arrive at this inequality, right? So let us start. So the first step is to construct a suitable function. So here we can take the function f of x, that is y is equal to f of x, and we can form the function as x minus natural log of 1 plus x square. So here we can take help of the inequality itself. If we take this natural log of 1 plus x square to the right hand side, we have x minus natural log of 1 plus x square. So we can take this function as f of x. Now let us find out the derivative of this function, that is dy over dx is equal to f prime of x. So here the derivative of x is 1, and the derivative of log of 1 plus x square is 1 over 1 plus x square, and by chain rule the derivative of 1 plus x square. So now we have 1 minus 1 over 1 plus x square, and the derivative of 1 plus x square is 2x, right? And remember the derivative of log function, that is d by dx of log of x, is given by 1 over x. So now we have this expression 1 minus 2x over 1 plus x square. So let us simplify it. We can take the LCM here, 1 and 1 plus x square. So we have 1 plus x square minus 2x divided by 1 plus x square. Now in the numerator we have a trinomial, and 1 plus x square minus 2x is equal to x minus 1 whole square. So here we have a minus b whole square is a square plus b square minus 2ab, right? So here we have x minus 1 square, and here we have 1 plus x square. So we can see that our derivative f prime of x is x minus 1 square over 1 plus x square. Now see, here we have a square term. So x minus 1 whole square is always going to be greater than 0. That is, this quantity is always going to be positive. And similarly here 1 plus x square is always a positive quantity, because here we have x square, right? So x minus 1 square is a positive quantity. Similar is the case with 1 plus x square. So our derivative, that is f prime of x, is always greater than 0 for x greater than 0. So we have shown that the derivative f prime of x is positive for x greater than 0. So the derivative is positive. So this implies that our function f of x, that is x minus log of 1 plus x square, is an increasing function, because a function is said to be increasing function if the derivative is greater than 0 or positive for the given values of x, right? Now here let us quickly see another definition of increasing function. If we have the axis, x-axis and y-axis, and if we have an increasing function, say y is equal to f of x, and if we take 2 points on this curve, that is say x1 and x2, right? So when x1 is less than x2, then this ordinate, that is f of x1, is less than this ordinate, right? So f of x1 is less than f of x2. So when x1 is less than x2 and f of x1 is also less than f of x2, then the function is said to be increasing function. So we'll now apply this concept to arrive at this inequality. So let us take x1 as 0 and x2 as x. So we have 0 less than x, right? So applying this inequality here, when x1 is less than x2, fx1 is also less than fx2. So now we have f of 0 is less than f of x, right? Now f of 0 can be obtained from here. So we have f of 0 is equal to 0 minus log of 1 plus 0 square, and this is minus log of 1, that is log of 1 is 0, so this is 0. So f of 0 is 0. F of x is given by x minus log of 1 plus x square, right? Now taking negative log of 1 plus x square to the left hand side, we have log of 1 plus x square is less than x, and this is our required inequality for x greater than 0. Hello viewers, in today's session we are going to discuss some important problems from application of derivatives. So here the problems are related to some important inequalities, and here with the help of the concept of increasing and decreasing functions, will prove these two important inequalities. In the first problem we have cos x is less than x plus 1, and in the second problem we have cosine of cos x is greater than sin x for all values of x belonging to the open interval, that is 0 to pi by 2. So here x varies from 0 to pi by 2. So we'll see how we can prove these inequalities easily with the help of the concept of increasing and decreasing functions. So let us start. So to begin with, we'll take the function f of x is equal to x minus cos of x, and x belongs to the interval 0 to pi by 2, right? So here we'll see that this function f of x is an increasing function, and to prove that this function is an increasing function, we'll first find out the derivative of this function, that is f prime of x is equal to 1. That is, the derivative of x is 1, then the derivative of cosine x is minus sine x. So we have 1 plus sine x. So the derivative of f of x is 1 plus sine x. And see, this function, that is sine x, is greater than 0, or it is positive in the first quadrant, that is when x belongs to this interval, that is 0 to pi by 2. So obviously 1 plus sine x is also greater than 0, or 1 plus sine x is positive when x belongs to this interval, right? So what we have seen here, the derivative is 1 plus sine x. Now sine x is positive, or it is greater than 0 in this interval, that is the first quadrant, and therefore this quantity, that is 1 plus sine x, because 1 is positive, so when we add two positive quantities we always get the third quantity as positive. So 1 plus sine x is also positive. So this quantity is greater than 0. So we can see f prime of x is greater than 0. So the derivative is positive, and this is the condition for a function to be increasing function. So when the derivative is greater than 0 or positive, then the function f of x is said to be an increasing function, right? So here let us quickly see the another definition of increasing function. Here we have the axis, and let us take an increasing function, say y is equal to f of x, right? And let us take 2 points x1 and x2 on this curve. So we have here x1 and this is x2. So this point A has coordinates x1 comma f of x1, right? And this point B has coordinates x2 comma f of x2. Now we can see that when x1 or x2 is greater than x1, because here x2 is greater than x1 and the function is an increasing function, then this ordinate, that is f of x2, is also greater than f of x1. So this is an important concept in increasing and decreasing functions, right? So when x2 is greater than x1, then f of x2 is also greater than f of x1 when the function is an increasing function. So we can write this expression as x1 is less than x2 implies f of x1 is less than f of x2, right? And here we have this inequality, that is x greater than 0 and less than pi by 2. So let us take x1 as 0 and x2 as x, right? So we have f of 0 is less than f of x. So let us find f of 0 from this expression. So f of 0 is 0 minus cos of 0. So this is 0 minus 1. Cosine 0 is 1. So we have minus 1, right? So here we have minus 1, and here for f of x we can write x minus cos x. So now we can take cosine x to the left hand side and minus 1 to the right hand side. So we have cos of x is less than x plus 1 when x belongs to this interval, right? So this is our desired inequality. Now let us prove the second one. So now to prove this inequality, let us take x1 as x and x2 as pi by 2. So we can now write f of x is less than f of pi by 2. Now let us find out f of pi by 2 from this function. So we have f of pi by 2 is pi by 2 minus cos of pi by 2, and cos pi by 2 is 0. So we have pi by 2 minus 0, that is pi by 2. So we can now write f of x is less than pi by 2. Now f of x can be replaced by x minus cos of x, and here we have less than pi by 2. So let us rearrange the terms. So we can now write minus cos x, and we can take this x to the right hand side. We have pi by 2 minus x. So now we have this important inequality. So now let us take the cosine of both these sides. So we have cos minus cos of x, and here we have cos of pi by 2 minus x, and here the direction of the inequality get reversed, because the cosine function, that is cos of x, is decreasing function in the interval that is 0 to pi by 2. Because when we find the derivative of cosine x, then the derivative is equal to negative sine x, and sine x is positive, so minus sine x is less than 0 in this interval. So the derivative of cosine x is negative in the interval 0 to pi by 2, hence cosine function is a decreasing function, right? So here when we take cosine of both sides, the direction of the inequality get reversed. So here a cos of minus cos of x. So here we can make use of an identity from trigonometry, that is cos of minus theta is equal to cos of theta. So here we have simply cos of x, and here cos 90 minus theta, that is cos of pi by 2 minus theta, is equal to sine theta. So here we can write sine x. So cos of x is greater than sine x in this interval. So this is how we can prove this second inequality.